So Kennedy from team, hello Connor, hello Spencer, hello August. Let's see you're connected. When I will be showing slides, let me know if you want to share screen or so the camera is fine. So okay, this is better. For the homework, please look on the recordings of last meeting. I'll try to save time and be a little quicker today. What were we doing last time? We were playing with a straw man, right? We did introduce the concept of density of states, and we were pretending that we all are the cavemen who do not have computers but know calculus. So we were deriving density of states for particle and one-dimensional balls. Suppose we are the same people without computers but with calculus, and we need density of states if the box is multidimensional, two-dimensional, three-dimensional. The idea of oligomers deals with one-dimensional box, right? It often goes here and there. But what if we have a graphene, which is like hexagonal benzene stuff plane? It's not a one-dimensional box. And if you chop it in a rectangular shape, it will be a box, but it will be two-dimensional. What if we have crystal where electron can go? And instead of carving a long nanowire, we carve it in a form of a thin film, flake, or cube. So it will be box, but it will be not one-dimensional, but two or three-dimensional. So in some sense, today's meeting is about pizza box and UPS travel box on quantum size. What were our mathematical strategy to get density of states? And I assume that we already remember what it is, how to define. So we were doing these three steps. First, plotting energy as function of quantum number, then inverting this dependence and making number of quantum states or number of occupied states that Stroman does see behind as function of energy, right? You remember? Right? So number of states as function of energy. And this function shows that as we increase energy, there are more and more states. If we take derivative of this function, we are getting density of states, right? And just in case, I see you in person, but just in case you have a wiping off all memory every night, which sometimes I do, density of states is the way to characterize large system with many electronic levels that humans cannot track by human eye. If there are 100 or 1,000 levels, one needs some integrated characteristics. Okay. So we are finishing, we are approaching to the finish of the third chapter. This is next homework, not on coming Monday, but next Monday. We are doing density of states, and your homework and our today's exercise will be just to mathematically provide a background and justify the following movie. So you see it's a box for poster. Now it becomes a pizza box. And as we progress through this movie, it grows into UPS box. So we do need to, I will run it once again, we do need to make a connection between shape of the box and density of states, which are composed of many levels. As you see, as it is approximately one dimension, it makes the shape. As it starts growing into two-dimensional, it creates shape that looks like a step. And as it starts to grow into three-dimensional, it becomes something like square root of energy. And I'll plot it once again. So originally it were discrete lines, then they combine together into this decreasing function. Then this decreasing function and combining together and form step, one step, another step. And then this stepwise structure moves to the origin and combine the steps connect to each other and form this ascending stuff. So if you understand what it is behind, if you can summarize it, you can stand up and leave the class. Basically, we will do nothing else. So here is the answer for your forthcoming homework on that is due on coming Monday. So basically, you need to generate 4 images like this and write a couple of sentences about each one. How do you interpret? And last homework was excellently completed by the class, but I noticed that amount of comments is approaching the limit of 0. So try to comment and interpret. And we will use this skill of describing figures later for the project and then presentations at the end of the class. So when we do have very, very small box, it is discrete levels. When the box is extended and looks like one-dimensional, it is a sequence of this shark teeth, which are unsymmetric. It goes sharply to the left and continuously it goes down to the right as one over square root of energy, right? As we proved last time. For the pizza box, it is steps. So in certain range, it is constant. It doesn't change as function of energy, which means the levels are equally spaced. There are same amount of levels per each energy interval. And for three-dimensional box, it grows as square root of something, of energy. Square root of some power, maybe not square root, maybe a little different power, but it's like ascending with less and less slope. Okay. So when we were here last time, we were looking at a straw man for density of states for one-dimensional. We are going to practice the same approach together. And I will spend most of the time of today's meeting for the two-dimensional thing. After we get through two-dimensional, three-dimensional will be really easy. So, do you see ugly handwriting? I hope you do. Do you see that it is in 2 colors, red and blue? So I'm just saving a little time of not writing it over. So the ugly writing in red corresponds to one-dimensional case. So it is solution of time independent equation. So wave function for one dimension is normalization constant sine n by x over size of the box, right? Energy is a set of constants n squared. What if we still have one electron and it is permitted to move in another direction? So if we live in rectangular space, the motion, there will be independent of motion of in x and y. Like it should be quite natural concept, but if it doesn't look natural, like if I throw something in the wall, I can, or if I take a gun and try to make a shot, I can provide acceleration, initial velocity in the x direction, and then it will basically go with linear velocity constantly, unless it experiences friction of the air. But at the same time, there will be gravitational force in y direction, right? And then after a certain time, it will move continuously on a line with constant velocity forward, and it will go with acceleration down. And after the time is needed to fall down on this like human height, it will fall down. So the bullet doesn't go straight. It goes sort of on a curve, especially if it is a long shot, or if it is a chem, or if you throw something, you know that things have a tendency to fall down. So if I throw something parallel to the surface, or if I shot with zero angle, and with another hand, I will just drop the bullet on the ground, or drop the tennis ball on the ground. The time is needed to for the ball to drop on the ground with x velocity and non-zero, and with x velocity equals zero, will be absolutely the same. So the motion in x and y direction are independent. If you do not have objections on this statement, then assuming that our wave function, our electron has 2 degrees of freedom, x and y, then in second dimension, it will also perform quantized motion. So it will be also signed. So now look at blue. Since it will be a different quantum number, it doesn't know what it does in x, we will call it nx and ny. And here we have ny pi y over L. It's probably can just correct this here. Blue color. I'm going to write the letter y to the best I can. So product of 2 signs, sine x and sine y, and the frequency or wavelengths, how dense are the fringes depends on the quantum numbers. Now, what about the energy? If it was a single particle in 1 dimension, the energy won't score as quantum number, right? If we have contribution to the energy, and in the box we have only kinetic energy. If it moves additionally in y direction, it will be just additive energy. So there is an additive energy with the same constant up front, proportional to square of this n sub y quantum numbers. So the state of an electron in 2-dimensional box is determined by 2 quantum numbers. Energy is determined by 2 quantum numbers. And wave function is determined by these 2 quantum numbers. One day, maybe even in this class, not this lecture, not next year, this year, this class, a few weeks later, we can plot product of 2 signs as 2-dimensional thing. It will be just like waves on the surface. But now we need to focus on the energy. So our goal is to check how many of these states will be distributed per specific energy interval. And through the movie that we were already watching, it should be flat, it should be constant. But who knows how this movie was done? Maybe I was artistically drawing it, snapshot by snapshot. As scientists, you shouldn't trust anything. So we need to prove it. So how to get from this red and blue equation to this density of steps? Density of states that looks like steps. Better. Let me quickly look into our online part. So Kennedy, Tim, Connor, Spencer, August, if you have any questions, feel free to ask or type. I'll wait a couple of seconds. And if there are no, I'm planning to go forward. Okay, no questions, but please do not hesitate. I'm here to answer questions, and it is one of the best activities. So, if we, I should take a tape and make a cross to select a spot every time again. So, how did we convert energy as function of quantum number into density of states like last time? We were inverting this dependence and getting number of states as function of energy, right? Quite natural. But if there are two dimensions, there are two quantum numbers. And we have only one number of states. So we need to combine two into one, right? So what is the idea? So we will use your, probably my background in middle school geometry or high school geometry. If we have a two-dimensional space and we have two coordinates, I'm going to invite you to auxiliary world where coordinates are not Cartesian coordinates in space, but coordinates are values of quantum numbers. So in nx and ny, two quantum numbers in space, and each state of the electron in two-dimensional box will be point in this strange auxiliary space. Make sense? Now, we are going to explore how the energy of the state affiliates with the position in space. And you already noticed, so it is nx squared plus ny squared, right? So based on your high school, middle school experience, if you have space with two coordinates and you have x squared plus y squared, or no matter nx squared plus ny squared, what does it mean?
Circle or ellipse.
Super. I do not know what I'm doing here. You can teach the course right away. Just take slides, look on what is shown. And so circle or ellipse. Very good. So based on Jared's insight, any point in this auxiliary space that sits on a line of circumference of the circle or ellipse will have the same energy, right? So once again, I see that everyone understands, but so any point on a line corresponding to the edge of a circle will have the same energy on one hand. On another hand, we need number of states with certain energy. So basically, we need to count how many states are on this edge line. Make sense? Whew. If you're not sure here or online, please give me a hint. I would be happy to comment. So we need to count number of states on the edge. This is my favorite image, and I'm trying to draw it every year, although next slide it will be already ready. So I just get relaxed while drawing. So if there are two dimensions and quantum numbers have only discrete values, then states of the particle in two-dimensional box corresponds to discrete points in this planar thing. Right? So if the sizes of the box in X and Y are fixed, we do not have freedom to point any position in this space. We need to be only integers, and X and Y. Now, according to Jared, and I really appreciate this, so we can draw radius and draw a circle. Since it's hard to pick literally on the spot, we will assume a width. So instead of H line, we will assume it is a H stripe. Basically, we need to count the number of dots in blue dots in the red stripe. And this will be number of states with given energy. And then if you have another value of energy, we can draw another stripe, another value of energy, and count dots there. So basically, we count dots as function of the distance. Right? And this distance in this auxiliary space will be related to the energy through some constant. And then we will just take express number of states as function of energy and take derivative. Okay. So one day I was drawing this way. Here is our old buddy straw man who goes forward and looks backwards and counts how many states he left behind. And here I'm just trying to give an example. If the point nx equals 4 and y equals 3, then this distance will be 3 squared plus 4 squared, 25 square root, distance will be 5. And then we count 1, 2, 3, 4. Right? And then we keep doing this exercise. Whew. Feel free to type or ask any questions, because I think we are going a little bit quicker than usual with ideas. Yes, please.
How do you determine the width?
I do not determine the width. If this is sufficient. So, as you were practicing in calculus, you said that things depend on epsilon parameter that later goes to 0. So when width is, when states are offset by substantial energy, we do not need the theory at all. We need it only if they are sparse, if the space so dense, so that no matter what is the width, it will be a continuous line. So we can, this trick is needed only for quite dense states or quite large boxes. If you are going to do practical computations or compare with electrochemistry or STM experiment, there are several factors that bring width in the real life. One of them is thermal broadening. So the energy of any quantum system changes with time because atoms are moving. And when they interatomic distances elongate and contract, energy fluctuates. And in average, it has width. So like KT, energy of thermal quantum is a good approximation for the width. But I do not do it here. So the number of states on this line is density of states. So if you can count them, and then as function of this radius in this auxiliary space, it will be already density of states. But we do want to do a little analytical derivation. So all states inside the circle is the number of states based on the practice of Stroman. So we need to make an equation for all states inside and then apply derivative. So to get an answer not specific for this picture, but in general. And now I need you guys to help me once again with your high school knowledge. If I have a circle of radius r, what is the area inside the circle?
2 pi r or
pi
r squared.
Super, thank you. So I told you, you can teach this course yourself. You do not need instructor. So the number of states will be pi r squared. And if we take on the positive numbers, it will be 1 quadrant with 25%, 1/4 of this pi r squared. So area with letter A, 1/4 pi r squared. Energy as function of quantum numbers, all constants, I don't care what they are, nx squared and y squared. If sizes of the box are the same, we can pull it into the constants. And this nx squared plus ny squared is just radius in this created space, auxiliary space. So you can call it radius squared, r tilde squared. So energy of particle in the box specified by quantum numbers nx and ny will be combination of constants times radius squared, right? We can identify the radius squared with pi/4 is number of states. So how can we combine these two things? This one equals to r squared with constants. This one equals to r squared with constants. This means that number of states and energy are equal with precision up to constant. So you can tell that number of states equals some constants times energy, right? No one objects, neither online or in person. And this is just a node. Radius is square root of energy. Okay, so we agreed that these two things are equal with up to a constant. So number of states, which means all quantum numbers with energy smaller than certain value of energy equals constant times just this value of energy. And density of states, by definition, is a derivative of number of states in respect to energy. Make sense? So if you take first derivative of this constant times energy over energy, the answer will be constant. Constant density of states means it will not change as we go forward in energy, so it will be flat thing. And we have seen it. There are steps. Something is happening when we jump from one step to another, but in the substantial region, we have many states, but they are spaced equally, which means density of states, number of states per energy interval stays the same. And I should repeat it later when we come to the end of the meeting, but in the it's kind of early conclusions, in the experiment scanning tandem microscopy and electrochemistry. Electrochemistry, often there are just few levels, so it is less applicable, although also connected. And specifically for STM, if we do have experimental way to measure density of states, which is available, then we as researchers may look on this density of states, how general trends, whether it has this decrement as square root of energy or this constant. And then based on this signature, we can immediately tell about the shape of the structure. So based on the spectrum, one can reconstruct what was the system. Main goal of spectroscopy and of characterization. So it is only first steps. To be more complete, we need to also consider three-dimensional case, but you'll see that there are specific features, signatures that determine or places allows to identify what was the dimensionality of the system. I think it is the same stuff, just one day I was playing accurate derivation of all this stuff. So number of states, here are all constants, which include size of the box times energy, and then by derivative, this constant will pop up as the DOS. So graphene, molybdenum disulfide, a nice bismuth telluride. Those are really hot topics that are being studied. And I think here are the examples of two-dimensional systems. So graphene, molybdenum disulfide, bismuth telluride, and lead halide perovskites were this lead and chlorine encaged between layers of organic spacers serve as a two-dimensional region where electrons can move freely if they have enough energy. And all these structures can be recognized just based on their density of states, if they are measured. So it is one of the 4 images that you're going to generate today in lab, and that you're going to report on Monday in your homework. And try to comment with more than one word, and maybe more than one sentence, maybe 1.5 sentences. What you see and how to interpret it. So further off with the strawman walking. Our strawman was successfully walking in one-dimensional space, two-dimensional space. Now it's time for three-dimensional space. Right? So you can extrapolate your experience in previous 15 minutes. So if in two-dimensional box, wave function was product of 2 signs, in three-dimensional box, it will be product of 3 signs. If the energy in two-dimensional box was nx squared plus ny squared, in three-dimensional box, it will add nz squared. So there will be 3 quantum numbers characterizing how quickly the particle is moving in each of the directions. Make sense? And also our experience from previous few minutes that radius is correlated with energy. So a space with an x and y and z, radius as distance from the origin, and then the surface will correspond to all states that have the same energy. But it is surface of the sphere. Make sense? So we are going to play the same trick to express radius as function of this an x and y and z, correlated with energy, then make inverse direction and take derivative. So what? No, I need to keep it tricky. This is really hard. You may or may not remember it from high school. If the radius determines energy, then number of states will correspond to all points inside the sphere, which means we need the volume of the sphere. So what's the volume of a sphere if you know the radius? Question number one, radius in which power will pop up in this three-dimensional problem?
Cube, right?
Yes. Basically, you did answer, and then there will be some factors up front. So something about pi, and maybe some fractions. Like
4/3, I think.
4/3 pi squared half cube. And since we allow quantum numbers to be only positive, we have 1/8. If you want to look great in front of some audience, you can tell we have taken 1 octant, right? Because it's 8 parts. Octa is 8 in one of the ancient languages, and then octant is like this little segment. So the radius cubed. The radius will be, again, the same story. It will be an x squared and y squared and z squared. And radius squared does correspond to energy, just by our rule of particle in the box. Energy and x and y and z is coefficients times radius squared. So if energy is radius squared, then radius is square root of energy. Right? No objections. So we replace radius cubed by energy into the power 1/2. The number of states will be a big constant because I'm so lazy to pull all this pi and stuff. So number of states as function of energy is constant times energy to the power 3/2. Feel free to ask a question, interrupted by voice or by message. And then, as soon as we have number of states, we get density of states as a derivative by definition. So we take derivative of e to the power 3/2. So what happens to the power of independent function when we take derivative?
Comes down, right?
Down by 1, right?
Yep.
So 3/2 minus 1,
1/2.
1/2. So e to the power 1/2. So density of states will be some constant times square root of energy. Right? And here are just the details if one really wants to skip all tiny details. So square root of energy, which means as higher up in energy you go, the larger is density of state, the more states are available for the electron. But the slope of this dependence becomes less and less. If you plot this function, as you already taught each other how to plot functions in math, you can define energy range and just plot stuff. So if you plot this function with dashes and then do some a little more detailed computational modeling for density of states by practical computation, they will coincide in some region, and then because of numerical errors, they may start to diverge, but it is nature of thinking in most computations. So this is probably the last out of the 4 images that you need to report in the homework due on Monday, with more than 1 sentence comment, how you interpret it. So 4 images. If the box is really small, it is just discrete levels, and for electrochemistry of small molecules, it's typically something like that. First reduction, first oxidation, and then it goes to the noise and no one cares. So it's mostly what is the energy of these peaks. When it is one-dimensional system, those are 1 over square root of energy, and they float Van Hoff singularities. They're very well experimentally observed, so-called carbon nanotubes. They're like brightly seen in measurements. So what we are doing here is objective thing. It's not just fantasy. So steps for flat models, and this 3-dimensional box, basically, if we have any material which is in bulk, which means infinite sized box, it often shows this dependence. So it's kind of universal law for density of states of solid materials. So what we are doing today, we are still at some intermediate level of learning the subject, but you already can make connection between the class and real life. And here is the movie once again, just to summarize what we did. So the first image is discrete levels for very small box. And as the box grows, it shows all the shapes that we covered. Thank you for your patience. Looking forward to see you at 5 p.m. and do not overload you with other courses. I will stay here a little bit to answer questions that came from online. Candidate team, Elmer, August. And if you do not have questions, you are very welcome to depart in peace. Thank you for this. Thank you.